Hello and welcome to another one of my videos about the derivative rules. In this video we're going to be looking at the rules for finding the derivative of the natural logarithm function and other related functions, but I'm not going to just tell you what those rules are. Instead we're going to see if we can figure out what the rule has to be. So what is the derivative of the function ln of x, the natural logarithm of x? Well, first of all, what is that function really? What does that mean? It's the inverse of the exponential function e to the x. So the ln of x, the natural logarithm of a number, is, by definition, it's the power you have to raise e to end up with that number. That is, y being equal to the ln of x means that e to the y equals x itself. So those two equations, y equals ln of x and e to the y equals x, are equivalent. They express the same relationship between x and y. So let's take e to the y equals x and differentiate. If e to the y and x are equal to each other, their derivatives should be equal to each other. Now remember, when you take the derivative of e just to the x with respect to x, you get e to the x. But thanks to the chain rule, if you take the derivative of e to the something, you get e to that thing times the derivative of that thing. So the derivative of e to the y would be e to the y times the derivative of y. So that's what we've got here, e to the y times dy dx, the derivative of y with respect to x, which is what we're ultimately interested in finding. And the derivative of x with respect to x would just be 1. Now remember, I said that dy dx was what we were trying to find, so I'm going to solve this equation for dy dx by dividing both sides by e to the y. dy dx equals 1 divided by, or over, e to the y. But remember, e to the y is equal to x, so this would just be 1 over x. So there we have it. The derivative of ln of x is 1 over x. And if we put that together with the chain rule, that means that if we have something else in place of just x, the derivative would be 1 over that thing times the derivative of that thing. So if u stands for any expression or function of x, the derivative of the ln of u would be 1 over u times the derivative of u. And we could also write that as just u prime over u, but it's more obvious how the chain rule is working if you write it as 1 over u times the derivative of u, because it's the chain rule that has you multiply by the derivative of the thing that you have in place of just an x. So let's look at some examples of using this rule. Suppose the function that we want a derivative of is the ln, that is the natural logarithm, of x squared plus 4. So remember, the derivative of ln of something is 1 over the something times the derivative of the something. Here that would be 1 over x squared plus 4 times the derivative of x squared plus 4, which would be 2x plus 0. And of course we could just multiply that together. On top we have 1 times 2x, which is 2x, and on the bottom we have x squared plus 4. So there's our derivative, 2x over x squared plus 4. Notice we've got the derivative of x squared plus 4 on top over x squared plus 4 itself on the bottom. What about if f of x is x cubed times the ln of x? This looks like a job for the product rule. After all, this function is a product. It does consist of two things being multiplied together, x cubed and ln of x. Remember how the product rule works. It tells us to take one factor times the derivative of the other factor plus the other factor times the derivative of the first factor. So first thing, x cubed, times the derivative of second thing, derivative of ln of x is 1 over x, plus the second thing its own self, ln of x, times the derivative of the first thing. And the derivative of x to the third power would be 3 times x to the second power. Now we can clean this up a little because x cubed times 1 over x would be x cubed divided by x, and that would be x squared. So we can write this as x squared plus 3x squared times ln of x. And there's our derivative. What about if f of x is the ln, the natural logarithm, of the sine of x? Notice how this is a composite function. We're doing something to x, and then we're doing something else to the result of that. First, we're taking the sine of x, and then we're taking the ln of that sine of x. So, remember the rule, the ln of something has a derivative consisting of 1 over the something times the derivative of the something. So here that would be 1 over sine x times the derivative of sine x, which is cosine x. And we could just write this as cosine x over sine x, and that would be equal to the cotangent of x. Now, I have been taking advantage of rules that you already are familiar with if you watched my other videos or learned about them somewhere else. So, the product rule and the fact that the derivative of sine x is cosine x and things like that are things that we have learned up to this point. So I am using them in working through these examples. How about this one? F of x is the ln of x to the 6th power. So for the derivative, we get 1 over x to the 6th power times the derivative of x to the 6th power, which would be 6x to the 5th power. If we go ahead and multiply those together, we get 6x to the 5th over x to the 6th, and that can be reduced. We can divide an x to the 5th power on top and on the bottom, and reduce that to just 6 over x to the 1st power. So that is the derivative. Now there's another way we could have done this. The natural logarithm function, or really any logarithmic function, has certain properties that you know about if you've studied logarithms. The logarithm of a product is the sum of the logarithms. The logarithm of a quotient is the difference of the logarithms. The logarithm of a power is the power times the logarithm. So anytime you see the logarithm of something times something else, you can split it up into the logarithm of the first thing plus the logarithm of the second thing. Anytime you have the logarithm of something divided by something else, you can split that up into the logarithm of the first thing minus the logarithm of the second thing. And like what we have here, anytime you have the logarithm of something to a power, that's equivalent to the power times the logarithm of the something that was being raised to that power. So here, we can rewrite ln of x to the 6th as 6 times ln of x. Now notice that is still f of x. I haven't differentiated yet. I've just used one of these properties of logarithms to rewrite the function that we want the derivative of in a different form. And now the derivative of a constant times a function is just the constant times the derivative of the function. So f prime of x would be 6 times 1 over x, or 6 over x. So notice that sometimes when the function that you want to differentiate is the natural logarithm of something, you might be able to use one or more of those properties of logarithms to rewrite that function in a form where it's easier to find the derivative. Here's an example. Suppose we want the derivative of the function f of x equals the ln of the expression x plus 3 over 7x minus 2. So Do you see which property of logarithms applies here? We have the logarithm of a quotient of something over something else, so we can rewrite that as the logarithm of the numerator minus the logarithm of the denominator. ln of x plus 3 minus ln of 7x minus 2. Now, each individual ln, we just use that rule. The derivative of ln of something is 1 over the something times the derivative of the something. So we get 1 over x plus 3 times the derivative of x plus 3, which would be 1, minus 1 over 7x minus 2 times the derivative of 7x minus 2, which would be 7. So really that would just be 1 over x plus 3 minus 7 over 7x minus 2. Now we could say, okay, there's the answer, there's the derivative, and just leave it like that. Or, if you prefer, we could go ahead and sort of combine those two fractional expressions, perform the subtraction, and put them all together. And if we're going to do that, we're going to need to get a common denominator. To be able to subtract fractional expressions, they do need to have the same denominator as each other. So to accomplish that, I would take this first fraction, multiply its numerator and denominator both by 7x minus 2. Take the second fraction, multiply its numerator and denominator both by x plus 3. And now they do have the same denominator. They both have x plus 3 times 7x minus 2 as their denominator. And so the result has a denominator of x plus 3 times 7x minus 2. And the numerator consists of 1 times 7x minus 1 times 2 minus 7 times x and minus 7 times 3. So 7x minus 2 minus 7x minus 21. And that can be simplified. The 7x minus 7x cancels out or adds up to 0. And the minus 2 minus 21 together is minus 23. So this turns out to be negative 23 over x plus 3 times 7x minus 2. So either one of those is a perfectly acceptable way of writing what the derivative is. Which one is better probably depends on why you're finding the derivative or what you intend to do with it. But what if we had not used this property of logarithms to rewrite the function before we differentiated it? What if we went straight ahead and say, hey, that's the ln of something. The rule is the derivative of ln of something is 1 over the something times the derivative of the something. Could we just do it that way? Well, yeah, we could. Let's see what happens if we try that. We would get 1 over x plus 3 over 7x minus 2 times the derivative of x plus 3 over 7x minus 2. Now, when we find that derivative, the derivative of x plus 3 over 7x minus 2, we would need to use the quotient rule, which would tell us to take the denominator, 7x minus 2, times the derivative of the numerator, x plus 3, so that would be 1, minus the numerator, x plus 3, times the derivative of the denominator. So the derivative of 7x minus 2 would be 7, and then that's all over the original denominator squared. Now that looks like kind of a mess. I do want to clean that up. So 1 over, or the reciprocal of, x plus 3 over 7x minus 2 would be 7x minus 2 over x plus 3. And then the second fractional expression has 7x minus 2 squared as its denominator, and its numerator is 7x times 1 minus 2 times 1 minus x times 7 minus 3 times 7. So 7x minus 2 minus 7x minus 21, which we've already seen simplifies to negative 23. Now when we multiply these two fractions together, there's going to be a factor of 7x minus 2 on top, and there's going to be two factors of 7x minus 2 on the bottom. So we can cancel or divide out a 7x minus 2 in the numerator and in the denominator, and what's left is negative 23 over x plus 3 times 7x minus 2, which does match or agree with what we got when we did it the other way. Now you can decide which of these you like better or think is easier, but I think this is a lot easier, especially if we stop right here. And this brings me to, I'm going to talk a little about something called logarithmic differentiation. And I'll admit that when I teach calculus, this is a topic that I don't spend a whole lot of time on. I sometimes present it as a bonus topic. It's something that you can get along without in most cases. It's easy to cook up examples where this is a really useful thing to be able to use. I'm not sure how often such examples come up naturally. But there are situations, like I said, I don't know how often they come up naturally, but I can certainly invent situations where this logarithmic differentiation takes a problem that would be difficult and complicated and makes it a lot easier. So, look at the question I've got on the screen here. Which is easier to differentiate? The function x cubed plus 7 times x squared minus 3x plus 12 over the square root of x to the fourth plus 6x plus 11, or the natural log of that same thing? Well, in the first case, if we were going to find the derivative of this, we would need the quotient rule, because it is a quotient. And when we use the quotient rule, it would tell us to take the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator all over the original denominator squared. So part of what we would be doing would be taking the derivative of the numerator, and we'd be using the product rule when we came to that part. And part of what we would be doing would be taking the derivative of the denominator. And we'd have to use the chain rule, or the fact that the derivative of something to a power is the power times the something to the power minus 1 times the derivative of the something, or the specialized version of that rule that applies when you have the square root of something. But it would get kind of complicated. We could do it, but we'd have to keep track of everything that was going on and apply all the applicable rules. What about if we had the ln of all of that? Well, at first that looks even worse. That gives you an even more complications to keep track of, because you'd have to take 1 over that thing times the derivative of that thing. But remember, those properties of logarithms can be used to rewrite that expression or function, to break it up so that products become sums, quotients become differences, powers become just multiplication by a constant. So basically things turn into other things that are easier to differentiate. So logarithmic differentiation is a way of taking an expression like this and using logarithms and taking advantage of those properties of logarithms to make it easier to find the derivative. So let me show you how that would work. If you want, you can consider this a bonus topic, but if you need or want to know how logarithmic differentiation works, here it is. I'm going to show you. So here's the function that we want to differentiate. We want the derivative of y equals, so we got a product, and we got a quotient, we got a square root. The whole thing is made up of x cubed plus 7 times x squared minus 3x plus 12 all over the square root of x to the fourth plus 6x plus 11. And like I was just saying, it would be easier if we were dealing with the ln, the natural logarithm of that expression. So let's work with that. Let's work with not y itself, but the ln of y, the ln of that expression. So first of all, the natural log of something over something else would be equal to the natural log of the numerator minus the natural log of the denominator. So I've rewritten this as the ln of x cubed plus 7 times x squared minus 3x plus 12 minus the ln of, and then I went ahead and rewrote the square root as x to the fourth plus 6x plus 11 to the 1/2 power. That means the same thing. And then where we have the ln of this product here, I can break it up into the ln of x cubed plus 7 plus the ln of x squared minus 3x plus 12. And where we have the ln of something to a power, I can rewrite that as the power, 1/2, times the ln of the something, x to the 4th plus 6x plus 11. Now, to find the derivative of this, it's not totally easy, but it's a lot easier because I'm not going to have to use the quotient rule. I'm not going to have to use the product rule. I'm not going to have to take the derivative of something to a power. I'm just going to use the rule about the derivative of ln of something is 1 over the something times the derivative of the something. Now, on the left side, what I'm taking the derivative of is the ln of y, the ln of y. So the derivative of the ln of something is 1 over the something times the derivative of the something. Here that would be 1 over y times, and I just wrote it as the derivative of y with respect to x, dy dx. And on the other side, we've got 1 over x cubed plus 7 times the derivative of that, 3x squared, plus 1 over x squared minus 3x plus 12 times the derivative of that, which would be 2x minus 3, minus, and remember, the derivative of a constant times a function is the constant times the derivative of the function. And for the derivative of ln of something, we have 1 over the something times the derivative of the something. So there we have 1 over x to the 4th plus 6x plus 11 times the derivative of that, which is 4x to the 3rd plus 6. So cleaning that up a little, performing the multiplications here, we have that 1 over y times dy dx equals 3x squared over x cubed plus 7 plus 2x cubed over x squared, or 2x minus 3 over x squared minus 3x plus 12, minus, and I went ahead and multiplied through the 1/2 times the 4x cubed plus 6 and got 2x cubed plus 3 over x to the 4th plus 6x plus 11. So this is equal to 1 over y times dy dx. What we really wanted was just dy dx. We wanted the derivative of that y function that we started with. If this is y, what is the derivative of y? What is dy dx? Well, to get from 1 over y times dy dx to just plain dy dx, what do we have to do? We have to multiply by y on both sides of this equation. So dy dx itself would be this whole business here, all times y. And remember, y is the function that we started with. So our final answer here is the 3x squared over x cubed plus 7 plus 2x minus 3 over x squared minus 3x plus 12 minus 2x cubed plus 3 over x to the 4th plus 6x plus 11 that we got here times the original function. And yeah, that is kind of a mess, but it wasn't all that hard getting to that mess. If we really wanted to, there might be ways we could simplify it. That would involve some more work. Or we could just leave it like this and say, okay, there's the derivative. So this was not an easy problem, but I think it was easier than if I had done it without the logarithmic differentiation and just attacked it directly. Anyway, that's the end of my discussion about logarithmic differentiation. What about other logarithmic functions besides the natural logarithm? So far, we've just been talking about the function ln of x, or ln of something, which is the logarithm to the base e. So that's a special logarithm where the base of the logarithm is the number e. But you can also have logarithmic functions to other bases. If you have a calculator with a log button on it, that probably means the so-called common logarithm or base 10 logarithm. So what about that function? What's the derivative of the function just log of x? Or what about the base 2 logarithm function, log to the base 2 of x, or log to any base of x? How would you find the derivative of a function like that? Well, there is a formula that you can use to change or translate from logarithms in one base to logarithms in another base. If you've studied logarithms, learned about logs in a class that you took before you got to calculus, this is one of the things you should have learned, that the log to any base of x is equal to the log to any other base of that same x divided by the log to that base of the original base. So this formula lets you convert or change from logs in one base to logs in another base. And in particular, this means that if you start with the base a logarithm, where a is any particular number, that's equal to the natural logarithm of x divided by the natural log of a. Once it's written in that form, we have rules that tell us how to find the derivative. I mean, after all, a is just some particular number. So the ln of a is a particular number. It's a constant. And 1 over that number is a constant. So what we really have here for our function is a constant, 1 over ln of a, times the function ln of x. And the derivative of a constant times a function is the constant times the derivative of the function. So here, for f prime of x, we get 1 over ln of a times 1 over x. So that's the rule. The derivative of log to the base a of x, where a is any particular number, is 1 over the ln of that number times 1 over x. Of course, if a were the number e, so that we were talking about base e logarithms, which are natural logarithms, this would be 1 over the ln of e times 1 over x. But the natural logarithm of e is just 1, so this would just be 1 times 1 over x. And putting this together with the chain rule, I can say that the rule is the derivative with respect to x of log to the base a of anything is the number 1 over ln of a times 1 over that anything times the derivative of the anything. What about other exponential functions? We already know that for the function e to the x, the derivative is just e to the x. But what about if we have some other number to the x power for our function? What about the function f of x equals 10 to the x power, or 2 to the x power, or just a to the x for any particular number a, whether it's 10 or 2 or 1.1 or 37 or whatever. So suppose that's our function. F of x equals a to the x, where a is a constant. It's just some particular number. We could also write that as e to the ln of a to the x. The e and the ln are inverses of one another, so they undo one another. E to the ln of anything is just equivalent to that thing. But one of the properties of logarithms says that the logarithm of a to the x is equal to x times the logarithm of a. So I can rewrite that ln of a to the x as x times the ln of a, or write those two factors in the other order. Put the ln of a first and the x second to make it obvious that what we have here is a constant, just a number, times x. If a is a constant, the ln of a is a constant. Now, we know that the derivative of e to the x would be e to the x, and we know that the derivative of e to the something would be e to that something times the derivative of the something, because of the chain rule. So when we differentiate, we get e to the ln of a times x times the derivative of ln of a times x, which is ln of a. Do you see why? The derivative of a number times x is just that number. The derivative of 3x would be 3, the derivative of 17x would be 17, and the derivative of ln a times x is just ln of a. And remember, by retracing our steps and working backwards, e to the ln of a times x is equivalent to just a to the x. So I can really write this as ln of a times a to the x. So there's our rule. The derivative of a to the x is the number ln of a times a to the x. And if you put that together with the chain rule, the derivative of a to any expression is the ln of a times a to that expression times the derivative of that expression with respect to the variable x. Now, I was originally planning to include in this video a discussion of the derivative rules for the inverse trigonometric functions. Arcsine, arctangent, things like that. But this video has already been long enough. I found enough things to talk about just relating to the logarithmic functions that I think I'm going to put that in a separate video. So we do still have that to look forward to, talking about rules for derivatives of the inverses of the trigonometric functions. See you then.